Hello, this is Programming Foundations with your lecturer, Mwila Nyurongo, for Lusaka Goldsmiths University. Today we are exploring the concept of iteration. This is another powerful way to add control to our programs, moving beyond the linear execution we've seen thus far. Our roadmap for today is fairly straightforward. We'll start with a quick recap of branching and strings from the last time. Then we'll look at why linear code isn't enough, the motivation for iteration. We will deep dive into while loops, move into for loops, and finish with some practical numerical examples like factorials and running sums. So in our last session, we introduced branching as a way to tell the computer not to follow code systematically or linearly. Instead of evaluating every line, branching allows us to skip around. Based on a condition being true or false, we execute one set of code or another. In Typescript, we implement this using the if, else if, and else keywords, defining our code blocks with curly braces. We also covered the string data type, which is a sequence of characters where indexing starts at 0. For input and output, we used prompt to capture user data, noting it always returns a string or null, and console.log to display our results. The key takeaway was Typescript's type safety, which catches errors if we try to use these types incorrectly before we even hit run. To understand why we need iteration, imagine a classic text adventure game based on Zelda's Lost Woods. The player enters the forest and is asked, go left or right. If they choose right, they see the exact same screen again. They are lost. They only exit successfully if they choose left. If we try to code this using only if statements, we hit a wall. How deep do we nest the code? If the user picks right 3 times, we need 3 levels of nesting. But what if they pick right 100 times? We simply can't predict a user's persistence when we are writing the source code. This is where iteration comes in. It is a control flow mechanism that allows us to repeat a task multiple times. Instead of hard coding every possible right turn, we want to repeat a set of instructions as long as a certain condition remains true. This makes our code efficient and capable of handling an unknown number of repetitions. The most fundamental tool for this is the while loop. It uses the while keyword followed by a Boolean condition. In Typescript, the syntax involves parentheses for the condition and curly braces to wrap the code block that we want to repeat. The logic follows a specific sequence. The Typescript runtime evaluates the condition. If it is true, it executes the code inside the block. Crucially, once the block finishes, the program automatically goes back to the top to recheck the condition. It only stops and skips to the rest of the program once the condition finally evaluates to false. You can visualize this as a cycle or a loop. As long as the yes path is taken, meaning the condition is true, the code block plays again. It is only when we hit the no path that the loop terminates and we move on. There is a major pitfall here, the infinite loop. If the code inside your loop never changes the variables used in the condition will stay true forever. Typescript doesn't always catch these logical errors at compile time, so it is your responsibility as a developer to ensure your loop has an exit strategy. If your program stops responding or starts printing X indefinitely, you're likely stuck. You have to manually intervene. In most terminals, you can use the Control-C or Command-C to kill the process. In your IDE, look for a red square, stop button, or something that says kill or terminate. If simple math is taking more than a few seconds, something is wrong. Let's look at the code for our Zelda example. We grab the user's initial input using prompt and save it to a variable called choice. While choice is exactly equal to right, we keep rerunning the prompt. The moment the user types left, the condition becomes false. The loop ends, and we log, "You got out of the forest." Keep in mind that string comparisons are case sensitive. If the user types right in all caps, the condition choice equals to right will be false, and they will exit the forest immediately. To make your code more robust for actual humans, a pro tip is to use the dot to lowercase method on the user's input. Loops are also essential for math. Suppose we want to print the letter X a specific number of times. We can initialize a variable, n to 4. While n is greater than 0, we print X, and then, this is the important part, we decrement n by 1. Once n hits 0, the condition becomes false, and the printing stops. A classic application is calculating a factorial like 4 factorial, which is 4 multiplied by 3 multiplied by 2 multiplied by 1. And to do this, we need a loop variable to act as a counter and a result variable to act as a running product. We initialize our product at 1 and multiply it by our counter in each iteration, incrementing the counter until we reach our target. Once you notice the factorial example, we used I plus equals to 1 and factorial multiply equals to I. These are shorthand operators. I plus equals to 1 is simply a more concise way of writing I is equal to I plus 1. Similarly, star equals, dash equals, and slash equals allow you to update a variable based on its current value with less typing, which is a very common pattern in professional code. Now that we've mastered the while loop, you might notice a recurring pattern in our code. We initialize a counter, we test it against a condition, and we increment it at the end of the block. This initialize test increment sequence is so prevalent that most modern languages like Typescript provide a dedicated structure for it, the for loop. While loops are superior when the number of iterations is truly unknown, like waiting for a specific user input, for loops are much more readable and efficient when you have a specific sequence or numerical range to iterate over. In Typescript, the for loop consolidates the entire loop management into a single line within the parentheses. The syntax consists of 3 parts, separated by semicolons: initializations, the condition, and the increment. This single line of code handles what previously took 4 lines in a while loop, making the intent of your code much clearer to anyone reading it. In Typescript, we explicitly define the start, stop, and step directly in the loop header. A standard range from 0 to 4 is written as let I equal to 0, I is less than 5, I increment. Or in other words, initialize I with 0, while I is less than 5, increment I at every step. While a custom range starting at 3 would simply be initialized as let I equal to 3. A critical detail to remember, and this mirrors what we've learned about string slicing, is that these ranges typically go up to but not including the stop value. If your condition I is less than 5, the loop will execute the values 0, 1, 2, 3, and 4. If your specific algorithm requires the number 5 to be included in the calculation, you must adjust your logic to use the less than or equal to operator, something like I is less than or equal to 5. We aren't limited to counting by ones. By modifying the increment expression, we can create custom step sizes. For example, if we want to iterate through every other number, we can use j plus equals 2. In a loop where j starts at 1 and goes up to 4 with a step of 2, j will take on the values 1 and 3. If we then print j multiplied by 2 inside the loop, our output would be 2 followed by 6. Sometimes you need to count down rather than up. To iterate backwards, you simply start with a high initialization value and use a negative step. For instance, if we initialize I at 4 and use the condition I is greater than 0, with the decrement I minus equals to 1, the loop will process the values 4, 3, 2, and 1. This is particularly useful for patterns like printing a decreasing number of symbols in each line. A very common use case for the for loop is maintaining a running sum. We initialize a variable mySum to 0 outside the loop. Inside the loop, we use the plus equals shorthand to add the current value of the loop to our total in each iteration. If we run this from 0 to 9, we are effectively calculating 0 plus 1 plus 2 plus 3 and so on till 9, which results in 45. If your loop isn't producing the expected result, don't panic, debug. One of the most effective techniques is inserting console.log statements directly inside your loop block to print the current value of your loop variable. This allows you to see exactly what the computer is processing at each step, which is often much faster and more intuitive than firing up a complex debugger for simple logic errors. To see the power of the for loop, let's compare it to the while loop version of the factorial program. The while version is quite verbose. You have to manually manage the counter initialization and the increment inside the block. The for loop version, however, is much cleaner and more readable because it encapsulates the loop control logic in the header, leaving the body focused purely on the mathematical calculation. In summary, iteration is our tool for repeating code without duplicating it. Using while loops when the number of iterations is unknown and depends on a dynamic condition, such as user input. Use for loops when you have a fixed sequence of numerical range to traverse. Regardless of the loop type, always ensure your logic makes forward progress towards the exit condition to avoid the dreaded infinite loop. The big takeaway today is that loops allow our programs to handle complex repetitive tasks with very few lines of code. While we've transitioned from Python's indentation-based blocks to the Typescript curly braces, the underlying mental model of how variables update in memory remains the same. Mastering this mental model is secret to writing bug-free iterative logic. Now that we have a solid understanding on basic types, branching, and iteration, we are ready to move beyond simple primitives. In our next session, we will begin looking at more complex data structures and how we can organize our code into reusable modules. See you then.